So welcome to office hours. We are Tuesday evening, December 9th. What can I do you for?
What can you do me for? I'm thinking proof by induction. I'm thinking proof by induction. I'm gonna look up a specific question that's gonna really get my brain going.
All right, proof by mathematical induction.
Induction. We
Yeah,
do a
it
special.
helps to have specific questions, but we can always look some up from the book if we need to. We can do whatever, we want to do with that.
I think I think it was off. It was one off of special homework that really kind of got me. It wasn't many special homework. It was special homework 9. That was special. That was proof by induction. Um,
Special homework number 9.
yeah, it was special homework number 9, question 4.
Okay, I'm,
Yeah.
I'm, I'm looking that up right now. So, oh yeah. So special homework number 9, problem number 4, we're asked to prove a product. So it's to prove that the product from I equals 2 to n of the expression 1 minus 1 over I squared is equal to n plus 1 over 2n. And that's going to be for n greater than or equal to what? Well, let's look at our lower limit of this product. The lower limit is 2. So what is the smallest that n could be?
And not is going to be 2.
That's right. Our n naught is going to be 2. Do you understand the general idea behind proof by induction?
Yeah, the general idea is to prove the basis, and then once we prove the basis, we can continue and move on to the next step.
All right. So in our proof by induction, we're just going to let P of n be given as above. We will not rewrite it because on the final, you're going to have it right in front of you and you're not going to want to rewrite it. So you can just say, hey, it's above. So what is our first thing, the first thing we should say when we start our basis?
I forgot when we were completely honest.
We need to tell our reader where we're starting.
And not okay.
So let n naught equal what?
And not equal to.
Great. And do you know what we wish to show is true?
We're wishing to show that um one minus. No, I don't know. I forgot.
Okay,
I
so
forgot
we
to.
wish to
Yeah.
show P of 2. Let's write down exactly what we wish to show, i.e., we wish to show that the product from I equals 2 to 2, n is 2, okay,
hmm
of this expression, 1 minus 1 over I squared, is equal to, now you tell me what the right-hand side uh, of P of 2 is going to look like. Remember, we've got a left-hand
Left hand
side.
side and the right hand side, and we have to prove that the outcome is the same on both.
That's right. So what would the right-hand side of P of 2
Be
look like?
n plus 1 over 2 n.
So, but n is going to be this value
Oh, excuse me. Yeah, 2 plus 1 over 2 n. Excuse me.
over 2 times 2. So that's our wish. Okay. Now we can't start with that equation. When we wish to show the equation, we're going to look at the left-hand side and figure out what it's equal to. And then we're going to compare that to what the right-hand side equals, right?
hmm
So what is the left-hand side of P of 2? The left-hand
Is
side of P of 2 is what?
is 1 minus, or technically 1 over 1 minus, um, technically it would be 2 over 2. Or no,
Oh,
excuse me, not 2 over 2. 2 to the power of 2. 2 squared.
yeah, yeah, 1 minus 1 over 2 squared, right? 1 minus 1 over 2 to the 2. And that, like you said a minute ago, is 1 minus 1 over 4. And what does that turn out to be?
I don't know. I need
Oh,
algebra.
oh, come on now. Listen, if you have a dollar and you give
Yeah,
somebody a quarter, what do you have left?
3/4.
Yeah. So the left-hand side of P of 2 evaluates to 3/4. Let's look at the right-hand side.
Oh, dirt.
Yeah.
Why am I so stupid?
That's okay.
Oh,
We're not,
duh.
duh.
Yeah,
Yeah,
that's
it
why I'm an
helps to
office
just
hours.
think real simply about quarters because it's, money. The right-hand side of P of 2, okay. So it looks like this, but 2 is here and 2 is there. So it's 2 plus 1 over 2 times 2. Well, what is that?
It's 3 over 4.
Great. So the left-hand side does equal the right-hand side, and P of 2 is true. So we just proved the basis. Now, we're going to move on to the inductive step or the induction step, where we assume that we're standing on step K, and our wish is to show that we can step up and stand on step K plus 1. Okay? So we let K, and where does K start?
And
Yep. So let K greater than or equal to 2 be some integer. It's not all integers, but it's just some particular integer. We don't know which one, but it's at least 2. And what do we assume? We needed an inductive hypothesis. It's always the same in induction. In the inductive step, we assume we're standing on step K,
so we assume that we're okay.
that P of K holds true. I.e., let's write down what P of K is. What are we really assuming? Well, just take this expression that's P of N and put a K everywhere we see an N.
So just be you would just be doing the same. So it would be
The product,
the product of um I would say I equals to
I equals 2 to what?
n.
Well, but N is now K.
That is k, excuse me, so it'd be k
Good. Of 1 minus
minus
1
1
over
over k
I
squared.
squared. It's
Oh,
still going to be in,
excuse me, I squared.
yeah, yeah, while the expression for the term is inside either the product or the sum, we keep the I, okay?
Okay, makes
And
sense.
we're gonna assume that that is equal to what?
It'd be k, or we're substituting every n for a k, so it'd be k plus 1 over 2k.
Perfect. Very nice. In fact, I'm going to put our little green box around this just as a reminder. Hey, this is like money in the bank, you know? This is our inductive hypothesis. And it's what we have in our hand that we're going to be able to use in a little while. Now let's write our wish. Okay, now that we see P of K, we'll easily be able to figure out P of K plus 1 because that's our wish. We wish to show that we can step up to the K plus first step. So we wish to show P of K plus 1 is true, i.e., all right, you tell me what we wish to show exactly so we can write it down and look at it.
It'd be the product of k plus 1.
We start at the bottom. The product
Oh, excuse
from,
me. It's product from I equals 2.
mhm,
And then on top you write k plus 1.
to K plus 1. Okay, good.
K plus 1.
Of
And then of you put 1 minus 1 over I squared.
nice. Good. So you understand it's still an I inside this
Yeah,
product. And that's going to have to equal what?
it's going to equal K plus one, but that's plus one. K plus one is is a binomial, so you put that. Yeah.
We
Make sure
don't
this is
actually need the parentheses because we're not multiplying K plus one times the plus one. We're adding it, but that's okay. It doesn't hurt to put the
okay,
parentheses
and
over
then
what?
over two, and then parentheses K plus one.
Yeah,
When you're
we need
multiplying,
the
we
parentheses
need the
on the
parentheses
bottom.
right there.
All right, that's our wish. All right, so just to remind us that this is a wish,
We'll put the curly
and yeah, our
clouds
little
on it.
dreamy cloud, right? That's our
Uh,
wish. And that helps us kind of not make the mistake of accidentally thinking we know this. This is what we know. This is our money
mhm,
in the bank. This is our wish. So we're going to work on this. We're going to start with the left-hand side of it, and we're going to work on the left-hand side and use algebra and our inductive hypothesis and some more algebra until it turns into the right-hand side. Okay?
mhm.
All right, let's get started with our inductive step. And we'll keep our inductive hypothesis up there where we can see it because we're sure going to want to be able to use that. So our proof continued. All right. So let's tell our reader exactly what we're doing. We're starting with the left-hand side of P of K plus 1, and we're going to turn it into the right-hand side of P of K plus 1. It looks like my green is running out. Looks like I need to
You might
get,
need another green marker. I mean,
yeah,
another
I'm gonna
pen.
need another green one. Let's see if I've got another green one. I will try that one, but I might need even another one. I go through a lot of green because I like to grade with green. Okay. All right. So starting with the left-hand side of P of K plus 1, what do we have?
We have the product. I'm sorry. I equals two, and then of K plus one. Let me make sure I'm right. I'm over here talking. One minus I equals two.
Yeah, I just scanned the notes from last night. The video's up, but I need to post the notes from last night. And I'll be sure and do that tonight before I leave my computer. All right,
Luckily,
so
luckily, I find that a lot easier than this, but it is a lot easier. All right, cool. And then we
now we're
put
going to use our
equals.
trick. Remember what our trick was about breaking off the K plus first term?
I don't remember.
All right, well, the point is, this is a really long product. Let's actually look at what this really is. This is 1 minus 1 over 2 squared times, because it's a product,
Uh-huh.
1 minus 1 over 3 squared times
Oh, I see what you're saying.
1 minus 1 over 4 squared times, keep on going. And the penultimate factor is the factor right before I equals K plus 1. What is I right before it is equal to K plus 1?
What is I before is equal to K plus one? It's just the basis.
No, we don't know how big K is. We don't know that K is just 2.
Okay,
It
you're
could
right.
be 103 or something. So it's just K
K is it
squared.
K?
And see what I mean? This is the factor that's right before the last factor. The last factor is when I takes on the value K plus 1. I'm just writing this out so you can understand what this left-hand side really looks like.
I see it.
It's a long product, but multiplication does not care what we multiply together first. We could take the product starting with the first factor, 1 minus 1 over 2 squared, times all the way up to the factor that is 1 minus 1 over k squared. You see, this product, we could figure out what that is, and then multiply it times the last factor. See, we split it up. This is the k plus first term. It's actually the
Mm-hmm.
kth term because we're starting at 2. But the point is, this is the last factor, okay? We can
I
group
got
it
you.
so that we're seeing the product from I equals 2 to k of this expression, 1 minus 1 over I squared. So this first part is the product from I equals, just say 1, I'm at 2 to k of 1 minus 1 over I squared. That is this
Mm-hmm.
times this last factor, 1 minus 1 over k plus 1 quantity squared. See, we can rewrite this long product as this product times the
Mm-hmm.
last factor. And there's a reason why we do that. Why do you think we actually do that? I'll put all this inside thinking notes. This is all thinking notes. We're just kind of figuring out.
Why do we batch it as
Yeah, why do we batch it? That's exactly what we're doing. We've got this batch here of things multiplied together with this
is it
last factor kind of hanging off the end. Why would we do that? There's a good
is it
reason.
because technically you can't quantify where K is?
We sure can't. And because we don't know what it is, we just know that it goes up to K.
K
But
just
don't we
kind of
know something about the product that goes up to I equals K? Like, don't we know something about this product from I equals 2 to K? Look at our inductive hypothesis. See, we got to assume something about that product from I equals 2 to K of 1 minus 1 over I squared. We got to assume, we did assume that that is equal to K plus 1 over 2K. See, we know something about what's going on inside the red parentheses here. We know that this product is the left-hand side of P of K. We know it's equal to the right-hand side.
uh
And that's why we break off that K plus first term, because then we can use our inductive hypothesis and substitute in right here.
okay.
And then we say what we're doing. We
It did, yeah.
always, yeah, this is by
Like by
induction.
induction.
Hmm.
Mm-hmm.
So what does this become then? All right, look at this. What is this? It's the left-hand side,
Left hand side
but we
of
know it's equal to the right-hand side. So can't we make a substitution there?
I think so.
Yeah, that's what induction is. It says we can assume that the statement is true, this predicate is true, when we have K.
Hmm,
So that means that this product that is just, these factors multiplied together is equal
is equal to K plus one. So
over 2K. That's right. We get to assume that.
uh,
So now that's where we're using that. And
so I can just okay, that makes sense.
see,
So I kind of just by induction, I can just go ahead and just move on.
and then we've got this broken off term that we will deal with. Okay, we're going to play the algebra game here in a minute, but the point is we have made huge strides just between this line and this line because now we don't even have a product symbol anymore. That's good because what we're shooting for doesn't have a product symbol in it, does it?
No, it does not.
And suddenly we've got, some fractions. That's good because what we're shooting for is going to be a fraction.
Yeah.
And so we just look at where we're at and we say, okay, this is where we are so far. We're shooting for this. Let's see if we can get from here to here.
Yeah.
And we've used our inductive hypothesis, so we don't even need to see it anymore, but we'll keep our eye on the prize. We'll keep our P of k plus 1 where we can see it because we're going to be shooting for this. See what I mean? We started with this and we're changing it.
Great.
We're, we're not changing the value. We're just playing algebra
Just
games.
manipulating it with
Yeah, we're
algebra.
just manipulating it. All right. Now, there are a couple of different ways to attack this, okay? Uh, I kind of like to deal with this first because I can't really see what this is until I get a common denominator. So
Mm-hmm.
we've got k plus 1 over 2k for one of the factors, but we're going to multiply it times whatever this is. What is the common denominator? If we're going to really try to subtract 1 over k plus 1 squared from this 1 right here, what is our common denominator going to be?
We want
Nope.
to.
All right, you're guessing. Let me help you. All right, this 1 right here is really over 1. Even though we don't usually write it over 1, it's really over 1. Do you
Yeah.
agree?
Yeah, I agree.
So when we're getting a common denominator, we look at the two denominators, and the simple naive thing to do is just multiply them together. The common denominator is the big one. It's the k plus 1 squared.
So the common denominator is a k plus one squared, but
Yeah,
it can't k plus one. I was thinking, can't k plus one squared just be written as k plus one times k plus one?
it can be, but we probably won't want to. Yeah, we can do that in a minute. But for right now, I mean, we can do that if you want.
Oh, which way is easier? That's the way I kind of want to do it.
That's fine. That's our common denominator. All right. Now, the 1 is over 1. We want
Mm-hmm.
to change it into something over k plus 1 times k plus 1. So what do we have to multiply the 1 times?
K plus one.
Times k plus 1. We have to multiply it times k plus 1 times k plus 1 because it's not over any of that. So we have to multiply it times the whole thing.
Mm-hmm.
Now this minus 1 is already over the k plus 1 squared, so we can just put the minus 1
I'll
there.
put the minus one.
All right, now let's simplify this numerator over here. We still got k plus 1 over 2k in this factor. All right, so let's multiply this out. K plus 1 times k plus 1 is k squared plus 2k
Plus two
plus
k
1.
plus yeah.
Yeah, if you use the FOIL method, k times k is k squared.
Mm-hmm.
K times plus 1 is plus k. But then we have plus 1 times k, so we've got a
Okay.
grand total of 2k. And
Uh-huh.
then plus 1 times plus 1 is the plus 1 here. But then we still have the minus 1.
Minus
Don't
one.
forget our minus 1. This thing is still over k plus 1 times k plus 1, right?
Yep.
All right. Well, the plus 1 and the minus 1
We're
cancel.
gonna cancel each other out.
So let's see what we're really looking at. We still got the k plus 1 over 2k, but this turns into k squared plus 2k over k plus 1 times k plus 1. Do you agree?
Yeah.
Now we're multiplying two fractions. This is
Yeah.
a factor of k plus 1 here. Like, even though we're writing it inside all those parentheses, we really don't need those parentheses anymore. We could just write it as we got k plus 1 on top over
And
2k
two k.
times k squared plus 2k over two copies of k plus 1. Do you agree?
Yes.
Well, guess what cancels? We got a k plus 1 on top, and we've got a
Yeah, we
couple of
can
copies. Yeah, so we can cancel with
cancel
one
it
of
out.
them. And you know how to multiply two fractions, right? If we're multiplying a over b
You have to
times
multiply
c
it.
over d, yeah, just multiply the
Yeah.
tops together, And
And
then
the bottoms.
multiply the
Yeah.
bottoms together. Yeah, I call it multiplying bikini style. Multiply the tops, multiply the bottoms. All right, great. So now this, becomes a one, right? Because we
Mm-hmm.
canceled k plus. So we've just got one times k squared
K
plus
squared
2k.
plus 2K.
So that's
2K,
just
that
k
stays the
squared
same.
plus 2k on top. And what do we have on the bottom? Well, we've got 2k
You can have
times
2K times
the other
K plus
copy
1.
of k plus
K
1.
plus 1.
Now, we're getting a lot closer to what we wish. This is where we're at. Hey,
Mm-hmm.
we've come a long way. We came from all this stuff to a single fraction. And we want a single fraction that's got a k plus 2 on top and a 2 times k plus 1 on the bottom. We are getting really close. What algebra do you think we could do? Well, we want 2 times k plus 1 on the bottom. We have a 2, we have a k plus 1, but we also have this k. So what might we be trying to do with this k?
Distribute it.
I mean, do we need it? Is that what we're going to want in our final algebra?
We don't, we kind of want to get rid of it.
We want to get
I'll
rid
be
of it.
honest.
So if we could cancel it with a k from the top, we'd be sitting pretty. Is there a factor of k up here that we could factor out so we can cancel?
I give it to,
How many k's are in k squared?
there's two.
Yeah. And there's a k in 2 times k. So
Yeah,
let's pull that k out. And what's left when we factor k out of k squared?
use KK.
And then
And
what's
then
left when we factor the k out of
use
this plus 2k?
itself or 1 or K.
Wait a
You
second.
factor out the 2 and you get out, you
We're
take out the
factoring
2.
out the k because we
Oh,
want to.
excuse me, you get 2. I'm tripping.
Yeah.
My
That's great.
I'm
And
so
then
bad
down
at
here,
that
we've
part.
got a 2 times a k times a k plus 1, right?
Yeah.
But now the k's do cancel. See? We got rid of the k on the
Mhm.
bottom. And now look what we've got. We've got k plus 2 on top, and we've got 2 times k plus 1 on the bottom. Isn't that what we wanted?
That's exactly what we wanted. We wanted to get to the point of
And
K
this is the
plus.
right-hand side of p of k plus 1. So keeping our eye on what we're trying to get helps us kind of like figure out, oh, I'm almost there, but I've got like an extra K. I better be able to cancel it. So let's factor a K out. And then that K downstairs went away. See what I mean? So
Yeah.
looking at your wish can help you figure out how to get there.
We just shimmy play games until it gets to the point where
Exactly. So in fact, we just proved that if we assume P of K, then we can get P of K plus 1. How did we get P of K plus 1? Perfectly legally. We started with the left-hand side of P of K plus 1 and we worked on it until it looked like the right-hand side. So we proved that the left-hand side is equal to the right-hand side of P of K plus 1. We proved P of K plus 1. And all we used was algebra and our inductive hypothesis, P of K. P of K was what we assumed, and we used it. We used it right here, and that's why we broke off that last factor so that we could make this substitution right here. See what I mean?
yeah, it makes sense.
And so then what's the last step to get full credit?
You have to say something smart about everything.
By the PMI. Invoke the PMI. Hey, Rock. Dog has been alerting. He is not a barker. He barks when there's somebody on the property, but sometimes he'll bark if he like smells a possum or a cat or something. He's got a really
Yeah.
good nose. So he's been alerting lately. I think that there's some animals out in the yard. By the PMI, we can now say that the product from I equals 2 to n of 1 minus 1 over I squared is equal to n plus 1 over 2n. We can say that is true for all integers n greater than or equal to, where did we start?
and not starting at 2.
Perfect. And that's proof by induction. So my suggestion to you is to go back to that special homework number 9 and work on some of those other problems, right?
Yeah.
And then you can take a nice scan of those and email them, and I can look at them. We can work
Of
another
course.
one right now if you want.
I would say give me a due later. I'll do the due later, and then but I think there's one more thing I want to talk about that I don't remember. Also, everything the final exam is cumulative, correct?
That's right.
So we're gonna get
You'll get a,
contrapositive
you'll,
and
yeah,
IO tables and stuff like that as well, right?
yes,
Okay,
yes.
cool.
And all the solutions to the tests are up. So, and there were two forms of each test, and they're slightly different. Some of the problems are the same, but some are different. And you can go and
Mm,
look at those,
okay.
So do later. Uh, prove that the sum from I equals 1 to n of I cubed equals n times n plus 1 whole thing over 2 quantity squared for n greater than or equal to 1. We can prove the sum from I equals 1 to n of, let me just think for a minute. Look at the book. Let's go to the book. And because we had some on divides too. Let's see, ebook, chapter 5, exercise set 5-2. There's a bunch of nice ones here. So we could prove the sum uh, from I equals 2 to n of, ooh, that's a hard one because it goes to n minus 1. I don't want to do that. Uh, that's a tough one because the upper bound is a weird expression. I mean, it's a good problem to try to do. You can go to the book for. But how about a number 5? The sum of the first n odds. So the sum from I equals 1 to n. Actually, yeah, the quantity 2n minus 1 is equal to n squared for n greater than or equal to 1. And then let's go and look for another one. See, you can even look at the solution. This is in the ebook,
Yeah.
number 5. This is the ebook, section 5.2, exercise number 5. And then a bunch of them. Yeah, this is number 11, but they don't have the answer. I really like number 12. That's a really pretty one. Um, I think number 18 we did in class. Look at number 16. Number 16 was the problem we just did. See how
Okay.
they wrote it in expanded form?
Yeah. Yeah,
Okay.
they wrote it how like
Yeah, they
the
wrote it
way to
out.
think about it, think about it
Uh-huh.
like that.
Uh-huh. Let's do number 12. we'll call that number three. We're going to prove, uh, we kind of want a product though too. Well, uh, number 12 is the sum from I equals 1 to n of 1 over I times I plus 1. How did I figure that out? Because they gave me the formula right here, 1 over n times n plus 1. That is the
It's
formula for the nth
essentially, yeah,
terms. So the formula for the ith term, just put an I here and here, and it's equal to n over n plus 1. I'll give you one more. This is yeah, they're not giving the answer to that, so it doesn't really matter. But number 18 is nice. And you can find number 18 in the class notes. It's to prove that the product from I equals 2 to n, not of 1 minus 1 over I squared, but it's 1 minus 1 over I. This is a really pretty one. It's equal to 1 over n for n greater than or equal to 2. This is for n greater than or equal to 1. So that's a lot of do laters.
that's good. That's good work. I think if I complete every
Oh,
one today,
yeah.
I'll be
If you do
on the
those,
test.
you are all
Then I'll be
set.
gold. Then I'll be golden.
You will be for
We'll
induction.
work on this tomorrow.
All right. So do you have anything else that you wanted to look at tonight?
I mean, not really, let me look at 8 point, like the other 8 point. I think we went
Binary
over 7.1.
relations.
Yeah,
Binary
let me
relations.
go.
Have you looked at the worksheet at all?
Yeah, I did work at the work. I looked at the worksheet. I didn't do it yet though.
Okay, well let's look at that worksheet on
Okay.
chapter 8. Okay.
Yeah. Oh, it's like curly R, and yeah,
Curly
definitely.
R.
Yeah.
Did you say crummy R?
No, curly, curly,
Curly
curly.
R. You said crummy R. That's funny.
Perfect.
So you got a couple where you just draw the directed graph, but you can always ask yourself questions, like, hey, let's look at R1. Even though I didn't ask you, is R1 reflexive? Well, what are the elements we need to see for it to be reflexive? We need to
I
see
forgot.
1, 1, 2, 2. What
Two,
else do
two,
we need to
three,
see?
three, four, to
3,
four, four.
3, and 4,
Oh
4.
yeah, if you're thinking about the graph or the things that we, like the little, the arrows that we drew out
Yeah, you would
for
have a
it to be
loop,
reflexive,
right?
you'd
You
have a
have a
loop at
loop,
every single point.
right?
Yeah,
So R1 would turn out to be reflexive. Is it
yeah.
symmetric? Well, if you have an
Symmetric.
arrow from 1, 2, you're looking for the arrow
Two,
from 2 back
yeah,
to 1.
two,
So that looks
three,
like but look at 1,
two,
4. We have an arrow from 1, 4.
one,
Do we have an
four,
arrow from 4 back to
one, four to
1?
one. Yes, we do.
Ooh,
But we
we
don't have an arrow
do.
from. We don't have an arrow from 3, 2 to 2, 3. So it's not.
Ah, you're
It's
right.
not
So it's
symmetric.
not symmetric. Good. So you'll be able to explain, hey, 2 comma 3 is in curly R1, but 3 comma 2 is not in curly R1. And here I ask you to write the definitions.
Okay.
That's good practice.
Actually, can we go over the
Yeah,
definition
let's go over the
of
definition.
transitive? I know the definition of R. I mean, they're in my notes somewhere, but like, I just want to re go over
Binary relations. And we only play this game, reflexivity, symmetry, transitivity, if it's one of the binary relations on a set A. In other words, curly R is a subset of A crossed with itself. That's the only time that it makes
it.
sense to play
Gotcha.
these three games. So here's our definitions. Curly R is reflexive if for all elements little a in set big A, we need to see little a, comma, little a in curly R, right? And if we want to write it using that, this is ordered pair
Mhm.
notation, right? Where we just talk
Yeah.
about the ordered pairs.
it would just be little a, curly R, little a, and a
Yes.
different in the other notation. I
Yeah,
forgot what
the
it's called.
relational notation.
I got you.
And I like
So
relational notation. But if we're checking ordered pairs, the ordered pair notation can be helpful. So it's for all little a in a. Like you said, little a is related to little a. Or you could say little a is curly R to little a. All right, so that's reflexivity.
yeah.
It's not an if then, it's just a statement. Little a has to be
Mhm.
related to little a. So that's reflexivity. R, straight R.
Yep.
RST, 1, 2, 3. So we needed one element to play reflexivity games. We need two elements to play symmetry games. So curly R is symmetric if we need two elements for all elements little a and little b in set big A. Do you remember the if-then definition for symmetry?
I don't remember. Or if A B then B A. C.
Yes, if A, B is in curly R, then B, comma A is in curly R. And if we want to use our relational notation for all A and B in curly A related to B turns around and implies that B is related to A. I meant to do this one in green. Oh well. I like I like to be I like to be consistent. I like to show the two different notations in two different colors just to sort of emphasize that these are two different notations. Okay, so while I'm rewriting the reflexivity definition, think about transitivity. How many elements do we need?
3.
Hmm. So it's a compound hypothesis for reflexivity. I mean, for transitivity. Transitivity. T.
If
Okay.
A B
Mm-hmm.
if A curly R B and B curly R C, then A curly R C.
Good. So if A curly R B and B curly R C, then together we cross over on the B, right?
Yep.
And we're looking for A to be curly R to C. This is our crossover element.
B and B is C. That means A must be related to C. Okay, I get it. I forgot what transitivity meant. Transitivity meant, but
But
just
now
meaning
you
that if
got it.
if A is B and B is C, then that means that A must be C because B is C and A is B.
And that means if we have, um, let's say A has four elements, 1, 2, 3, and 4. If we have, say, an arrow from 1 to 2, and we have an arrow from 2 to 3,
2, 3.
if one is related to two and two is related to three, what kind of arrow do we need?
That means we need an arrow from 1 to 3.
That's right.
Doesn't matter if it's from 1 to 3 or 3 to 1.
It does matter.
Yeah,
It definitely matters because just because one is related to three, that doesn't mean three is related
yeah,
to
they're
one.
related to 1. You're
Yeah,
right.
see, that's symmetry for you. The relation may not be symmetric. We
Yeah, it
might
could be
see,
transitive, but it won't be symmetric. Symmetric.
oh, it can be. It can be symmetric.
If there's other times where I'm going to have symmetry and I'm going to have transitivity.
Yeah, yeah. In fact, here's a really good game to play. We've got these three properties, right? R, S, and T, right? So find a binary relation on A, and all you need is four elements to play all of these games. That is, well, one, two, there are 8 different flavors. There are 8 different ways that we can mix and match reflexive with not symmetric or reflexive with symmetric but not transitive. So here it's R and it's S and it's T. In fact, comma is not such a great, we want it to be R and S and T. So it's reflexive, symmetric, and transitive. That's what I mean when I say it's R and S and T. But what about find one that's R and S and not transitive? See if you can find one of those, and you will be able to. You can find one of each, reflexive, symmetric, and not transitive. All right. Or it could be R and not S and T. You understand what I mean when I say that, right?
Reflexive and transitive, but not symmetric.
Right. Or it could be R and not S and not T. Or it could be not R and could be S and could be T. See, it's like we're making
You just, yeah, I feel it.
an IO table where if you got a 1, it means it has the property. If you have a 0, it means it doesn't have the property.
Exactly.
And we've got 8 different ways to fill in the inputs of an 8 row, 3 inputs, an 8 row truth table
This is literally just a
or
truth
IO
table.
table. Yeah, yeah, that's exactly what it is.
Oh, truth tables, that's going to be on our front again as well.
Or IO tables or both. So then we
Okay,
want
okay.
not R and S and not T. What would be another one? What would be row 7?
It'd be not R and not S, but T. But you have T, and
Nice.
then there would be not everything. So it's not reflexive, it's not symmetric, or not, or and it's not transitive.
Yeah, man. If you do that, you'll be golden.
Okay.
It's fun. Like, let's see if we can do number 3.
You could definitely do number three.
Let's do 3,
I
just
think
for
you
fun.
you just did number three, but
Oh, did we just do 3?
well, it was reflex. Well, no, we didn't have any reflex. We had
Well, it
transitivity, but
wasn't
we
reflexive, was
it
it?
wasn't reflexive. Yeah,
But we could easily
so
make it reflexive by just
make it reflexive
adding
by
those.
adding those, and then
Right, right.
yeah,
So let's just take a look and see if we can read off how to do it. Let's do 3. So we want R and S and not T, right?
yeah.
All right, so curly R. We'll call it R3. And our set has got 4 elements. Okay, here's the fourth one. A's got 4 elements. So what are some elements you want to have because we want reflexivity?
For reflexivity, you're gonna want one and one. You're gonna want two and two. You want three and three and four and four.
Okay, so we've got reflexivity. Great. Now, oh, this one, wait a minute. It's not S and not T, it's not S and T. It- Number 3 was,
Oh, excuse me.
yeah,
Number
yeah,
three is not S, but it's not symmetric, but it's transitive and reflexive.
yeah.
Yes.
And this was transitive, right?
Yeah.
So what are the ordered pairs that we're seeing here?
We see one and two, we see two and three, and we see one and three.
So it's transitive. These elements never make transitivity go bad. Remember, we never have to
Yeah,
worry about the
reflexive
reflexive elements.
elements never
And they
make
never make
transitive.
symmetry go bad either. So it is transitive, but it's not symmetric, right?
Yes, not symmetric.
So, it is transitive. And how would we, verify that it's transitive? Verifying that it's reflexive is easy, right? You know, A comma A is in curly R3 for A equals 1, 2, 3, and 4.
3 and 4.
So, that's easy but transitivity can be a little bit of work. But since we know we don't have to worry about these elements, these are the only elements we have to worry about. So 1 comma 2 is in R3 and 2 comma 3 is in our R3, but oh, wait a minute. It is, it is, yeah.
Yeah,
Sorry.
and
I must be not firing on all cylinders. That does imply that 1 comma 3 is in R3, right? We did get
mhm.
it. 1 comma 3 is in R3. All right, let's just double check and make sure we didn't mess it up any other way. Was there any way to cross over on anything else? Nope, only the 2. See, only the 2 appears as both a second coordinate and as a first coordinate. That's
Mhm.
the only time that we are going to satisfy the hypothesis of transitivity is if we have some element of A, here it was 2, that appears both as a second coordinate and as a first coordinate, ignoring these, of course.
Okay.
Like 1 only appears as a first coordinate. 3 only appears as a second coordinate in these ordered pairs that aren't reflexive ordered pairs. So we don't have to worry about trying to cross over on 1 or on 3. But the 2 appears both as a first coordinate and a second
Mhm,
coordinate. So we
mhm,
do
mhm.
have to worry about crossing over on the 2. And
Mm,
is it symmetric?
no,
And that was because why?
because we have 2, 3, but we don't have 3, 2.
Yeah, 2, 3 is an element of
Mhm.
R3, but 3, 2 is not
Same
an
thing with
element of
same thing
R3.
with 1, 2. I mean, you could pick and play how you want to do
Or
it.
you
You have
could do
3,
1,
1.
2 or 1, 3,
Yeah,
right? So so that was just, one of them. So now do the other 7.
mhm.
Build a relation for the other 7. And the key to doing it is to be minimal, like keep it simple. Don't start throwing lots and lots of ordered pairs in there because then it's going to make it really hard to check stuff. Just try to do the job with a minimal number of ordered pairs.
I got you.
Did you know that the empty relation is symmetric and transitive?
An empty relation,
Yeah, by false
like
hypothesis. Yeah,
I
there
didn't
is
know.
there is a subset
Write
of
that
A
down.
cross A called the empty subset, right? By
Yeah,
definition, the
empty set.
empty relation is a binary relation from A to A. So that's an interesting fact. It's worth just saying a few words about. So given A equals 1, 2, 3, 4, here's a fact. The empty set is a subset of A cross A, right? Because the empty set is a subset of every set. So by definition, the empty set is a binary relation on A. That's a fact. Here's another interesting fact about the empty relation. The empty relation is a symmetric binary relation on A. In fact, it doesn't even matter what A you pick. It's a symmetric binary relation on any set. Why? Well, let's look at the definition of what it takes
That means that
for
you need
a binary relation, yeah, to be
you need
symmetric.
A curly R B and you need B curly R A.
Yeah, it's an
No
if-then
matter what,
definition, isn't it?
you get not.
If A is related to B, then we need B is related to A. But
No,
is there any A related to B in the empty relation?
no.
Right. The hypothesis of the definition of symmetry is that A is related to B, right?
Hmm.
It's only if A is actually related to B that we need to check that B turns around and is
So it's
related to A.
my false truth.
Yes. So the empty set is symmetric by false hypothesis because there is no A related to any B.
Makes sense.
There is no A comma B in the empty set, which is the same thing as saying A is related to B. I mean, it's just two different notations for the same thing. So what other property do you think the empty relation is going to have?
So it's probably going to be transitive
It
by false
is,
hypothesis too.
yes, the empty relation is transitive, also by false hypothesis. Isn't
You
that
need,
interesting?
yeah, you need A related to B, but if you don't get A related to B, then you get automatically assume by false
Yeah,
hypothesis.
there is no A, B in the empty set and B, C in the empty set. You would need both of these to need the A, C.
Yeah, you need the if, or you need like the assumption.
Yeah, you need the hypothesis to be true in order to have anything to check. And if then is true when the hypothesis is false. So some of these 8 different flavors, some of them we can get. Well, there's one of them that we can get with the empty relation for sure.
Which is, yeah, number one is the empty relation.
Because we got to have those 4 elements to get R.
Oh, geez.
But if we don't need it to be reflexive, then the empty relation is going to be not reflexive because it's not going to have any of those required 4 ordered pairs, right?
Yeah,
But it
you're right.
will be symmetric and it will be
Okay,
transitive.
transitive. So
So,
you get number five.
yeah. So R5, which is not R and it's S and it's T, could be that R5 is just the empty set. If we call this one, R1 and we call this one R2 and this one R3 for
Three.
obvious reasons, right?
Yeah.
Then you get did I say 2, 6? Hey, by the way, how many binary relations are there on A? So here's just a question for thought, food for thought, good food for thought. And then I'll leave that question with you. You can think about it and we can talk about it next time. By the way, tomorrow office hours are in person in my office
Yeah,
because
I
I'm
saw.
going to try to give stuff back to people.
All right,
Um,
I'll be there.
right. If A has 4 elements, and that's kind of my favorite A, right? That has 4 elements because we can do everything we want to do with that. How many different binary relations on A can we find? So let's just think. I'm just going to give you a hint. By definition, a binary relation on A is any subset of A crossed with A, right? Because all these binary relations are sets of ordered pairs where the first and second coordinates come from A. So binary relations on A are subsets of A cross A. So you can think about it and it will blow your mind because there's a lot of them. All right.
I got you. All right.
Thanks for playing.
I'll be here tomorrow. I'll be actually, where's your office?
It's on the third floor. It's Dr. Good's office, so it's in person on December 10th, and it's York Road 367. It used to be 345, but we changed office numbers,
All right.
and that'll be from 2:30 to 5:30.
35:30. I'll be there sharp 2:30.
All right, I'll be ready for you, man.
All right. Thank you so much.
You're so welcome.
All
Have a
right.
good
Have a
night.
good night.